still recording yet? Hi, greeting everyone. Let's talk about the elements of the periodic table. So there are 118 of them, right? When I did my SDPM, we know that there were 118, but the last 8 of them didn't even have formal names. So now they have formal names already. So number 1, hydrogen. Alright. Then at the other end you have helium. 3, lithium. Lithium. Then we talk about beryllium. Now, why do you even bother know this? Well, one, we want to show off. The other thing is actually a lot of these things are very common. See, a lot of all these things you actually come across in your study of medicine, but you never bother to look deep into them. And then after that, at the other end, so you have boron, carbon. Okay, carbon is so important because we are all carbon based, and even the most important source of energy is what does carbohydrate means actually? Carbon and water, because the formula for carbohydrate is CH2O N, correct? So it's actually carbohydrate, water. Carbon that has water stuck to it. That's it. That's basically what sugar is. Carbon and then nitrogen, excellent. Oxygen, okay.
Fluorine.
Yes, actually, fluorine, very good.
Neon.
And then you have your noble gases stuff. So neon, okay, argon. It would be very important, especially argon. Why is argon important? But we'll talk more about that later. Krypton. Okay, what else do we have? Xenon. Not Xeon. Xenon. Hey, the guy in CF is known is
Xenon.
Xenon. How do you spell the Xenon?
Xanon.
It's almost like Xenon. Radon. And the last one is actually organoson. This is this 118. It's 118. Alright, let's build out lithium, sodium, potassium. Someone what else? Rubidium, cesium, francium. Excellent. Francium is named, the person who discovered is actually a lady, and she was doing a PhD. So of course guys have to joke about girls lah, but there are exceptional female scientists out there lah. They're rare, but they are out there. Marie Curie and of course the lady who discovered francium. Okay, beryllium, magnesium, calcium, barium. Okay, strontium. Okay, barium. Can you give me something to? Sorry.
You want something else?
No, I don't want the drum tenses me. Can you give me a tissue? The tissue, just the hand towel. That would be most helpful. Okay, calcium, strontium. Okay, barium, and radium. Radium was the one that's discovered by Marie Curie. Okay, the ones because it's radioactive, so that's why it was called radium. Alright, and then after that we go boron, aluminium, silicon, phosphorus. Okay, phosphorus. Okay, sulfur.
Chlorine.
Chlorine. Your sodium chloride, chlorine, bromine. Okay, iodine. Okay, astatine. Okay, and tennessine, named after the state of Tennessee. Okay, oxygen, sulfur, selenium, tellurium, polonium, named after Poland, which again where was Marie Curie from, and livermorium. Liver after Livermore in Tennessee because it was where the Livermore laboratory was. That was where it was made. Nitrogen, phosphorus, arsenic, antimony, bismuth. Okay, bismuth again. Remember, very important. Moscovium. Russia is one of the places that do a lot of this high energy because they bombard and they made a lot of this. So organoson is a Russian scientist, Moscovium and all. Silicon, carbon, silicon, germanium. This one is used in your chips. Stannum is your tin, plumbum. Okay, lead is very important. and this is your Roentgenium. Okay. No, sorry, Flerovium. Flerov was the another Russian scientist. Boron, aluminium, gallium, indium. Okay, indium and thallium. Okay, and then this one will be nihonium, named after Japan. Nihonium. Okay, Nihona. Okay. Then after that you have your 3, 4, 5 and 6. So what were your 3, 4, 5 and 6? Okay, so you have your scandium, named after Scandinavia, titanium, okay, and then vanadium, chromium, okay, manganese. Manganese is very important, again one of the essential. Iron, okay, cobalt, nickel, copper, and you have zinc. Again, one of your, okay, so we will talk about all those and more. Okay, scandium, yttrium, and then you have your lutetium, titanium. Titanium, you have your zirconium, hafnium, okay, vanadium, niobium, tantalum, chromium, molybdenum, and tungsten, also known as wolfram. In Germany, they name it wolfram, but tungsten won out. Manganese, technetium, and this one would be your rhenium. Okay, iron, ruthenium, okay, and osmium, cobalt, rhodium, okay, and iridium. Okay, nickel, palladium, platinum. Again, this one is very important. You see all these like, hey, why there are so many? But you actually come across it a lot in your medicine. So we don't learn it. Of course, we learn it to show off. But yeah, argentum, okay, and then gold, okay, aurum lah. Okay, zinc, cadmium, okay, mercury. All right. So this would be your 3, 4, 5, the ones in the middle. Okay, and then after that you have your lanthanide series, and then you have your actinides. Okay, so lanthanide series, lanthanum, okay, cerium, praseodymium, neodymium. This one is also another one. Promethium, samarium, europium, gadolinium, small garden terbium, disoprium, holmium, herbium, thulium, ytterbium. Okay, your actinide series, actinium, thorium as in Thor, thunder god, proactinium. Okay, and then proactinium, americium.
Uranium.
Uranium, uranium, neptunium. Okay, plutonium. Okay, and then your americium. Okay, curium, name of the Curie family. Berkelium, Berkeley in California, and californium. Okay. Mendelevium, after Mendeleev, who was like, okay, Einsteinium, fermium, mendelevium, okay, nobelium, and Nobel-Lawrencium. And then at your last row is your last row with this is your Rutherfordium, and Dubnium, Seaborgium. Seaborg is the name of Nobel Prize winner. Then you have Bohrium, okay, Bohrium, Hessium, Meitnerium, okay, and then you have your Dunstardium, and then Rothernagium, and Copernicium. Okay, so the ones towards the end not much use for that because all these So let's talk about hydrogen. Okay, hydrogen used to make water is essential for life. Okay, your sun is also made from hydrogen, so we derive all our energy from the sun. So sun is stored in the plants, we eat the carbohydrates. Okay, helium is very important. Helium is the light. Hydrogen was used to fill balloons, but it was very flammable and everything exploded. I'm sure you heard. Helium is next to lighter, so you can use to fill balloons. Okay, so where does your voice sound a bit like when you breathe in helium?
Because at the speed of how we move on.
Because it's less dense. So when my voice sounds this way because this is the density of the air. But when I breathe in my mouth full of helium, it's less dense. So that's why my voice is a bit high pitched. Of course, helium is used, of course, in cooling. The supply of helium in the world is limited. So your MRI actually needs a lot of helium, liquid helium, to actually cool the magnets. Okay, lithium. Alkaline metal, earth metal, yeah, is used in treatment. If you have a thyroid storm, sometimes you actually give the patient lithium. You're bipolar, also you give lithium. Okay, lithium when you're given in high doses will cause a nephrogenic diabetes insipidus because it prevents the binding of the vasopressin to the kidney, so you'll be pouring out urine a lot. So lithium is actually very, very important. Other than the fact that you use it to, you put in water and the whole thing explodes out. I think you do it in your Form 5. But actually lithium is also one of those essential things that we use a lot. Beryllium is what causes?
Berylliosis.
Berylliosis is a form of?
Interstitial lung disease.
No, it's not. It's pneumoconiasis. So what's the difference between extrinsic allergic evelitis, occupational asthma, and pneumoconiasis? Since we are in the subject of berylliosis. And then radon is also one of those occupational lung disease. So all of them are actually under the category of occupational lung disease. They are, okay, they are what you get exposed. You do your occupation, you're exposed to it, and then so your occupational lung disease. So of course you have pneumoconiasis, extrinsic allergic alveolitis, and then you have occupational asthma. Alright, a lot of the things that causes occupational asthma may also cause extrinsic alveolitis. Alright, so pneumoconiasis is something that causes after 20-30 years. Whereas extrinsic allergic alveolitis and you have a subacute phase, you get a fever because there's a sensitization period, a subacute sensitizing phase, and then after you have the chronic phase. So the symptoms appear within weeks to months after exposure. Whereas pneumoconiasis patients is asymptomatic for 20-30 years. They all lead to fibrosis like pulmonary fibrosis, pulmonary hypertension, copulmonary, and death in the end. Okay, but the time, alright, pneumoconiasis, okay, you get the fibrosis. Extrinsic allergic alveolitis, why? So it's in the alveolus. So you have thickening at the alveolus, so your DLCO will go down and you get a shortness of breath, dry cough. Whereas asthma is in the bronchus. Asthma is about bronchial area tightening, increase mucus production. So you get wheezing. You have a wheezing, you have a cough, which is one of the signs of asthma. So these are the difference between occupational asthma, extrinsic allergic alveolitis. So beryllium is causes berylliosis, which is a pneumoconiosis. Alright. Boron, used in some of the enzyme, you use more boron carbide plates. Okay, biologically not so important. Okay, carbon, we are all carbon based. Okay, carbohydrate, everything. The whole biochemistry is organic chemistry. Okay, organic chemistry is any chemistry that's dealing with carbon. Nitrogen, again, essential for life. You need to make proteins and all. They have a
Amine and?
the amine NH2 law. So without nitrogen, we cannot live. So we need nitrogen. Nitrogen provides us with all the nutrients or proteins full of nitrogen. Okay, oxygen, of course, we breathe using oxygen, but oxygen is actually toxic because oxygen radicals leads to premature aging, and also you need oxygen, but oxygen in a moderate amount. Okay, fluorine, used in fluoride, strengthen your teeth. Neon, we don't use it so much. Neon, use it for neon lighting. Sodium, essential for life. Hyponatremia, your muscles will be weak. Okay, hyponatremia, too much salt. So again, sodium is essential for life. Magnesium, also another essential for life. Okay, and magnesium, hypokalemia. Hypomagnesemia causes hypocalcemia, causes hypokalemia. Why? Because it's actually essential for in your kidneys for the reabsorption of both these two things. So if you hypocalcemia, you give how much calcium also. If you do not correct the magnesium, it will not correct. You're hypokalemic, you don't correct the magnesium. That's why magnesium, people like, hey, why people always take magnesium together with potassium and calcium. Why? Because you need to correct the hypomagnesemia before you can correct the hypokalemia. If not, you see them, they keep on giving the potassium and they never improves. Why? Because you never solve the underlying problem. Okay, alright. So then aluminium is a poison. So if you cook with aluminium pots, you actually can get dementia. So in the old days, there's actually a lot of aluminium in the water. They use the normal pipe water for the dialysis. So a lot of the patients on dialysis actually develop aluminium toxicity. Only now they use the reverse osmosis. So aluminium and yeah. Okay. Silicon is used in your computer chips. Again, not so much for us medicine. This is our interest. Germanium also is used in your computer chips.
Implants?
Huh?
Implant?
That also, but not so important. Only you are thinking about it. I didn't even think about it. Phosphorus again. Phosphorus very important. Your ATP and all are all recurrent. They are all derived from phosphorus. Phosphorus is used to store energy. So you need your ATP and all. Alright. So one of the more important things. What's the difference between a nucleobase, nucleoside, and a nucleotide? Basic biochemistry.
The base is the nitrogenous base.
Okay, the nitrogenous base. So your purine and all, they are the base stuff. So purine is your guanine and your adenine, guapo, GAPUR, guanine, adenine, guapo, cut a pair, CUT, cytosine, uracil, and thymidine is your pyrimidine. Alright, sulfur again, essential for life. A lot of the things, hydrogen, sulfur, and all. Chlorine, your sodium chloride. Again, in your body is also one of the things in your body, chloride. Alright, so if I give you too much normal saline is actually not normal, it's higher than physiological. What will happen to you? You have too much chloride, so your body will try to get rid of it. But when it gets rid of chloride, what does it do? It reabsorbs the hydrogen ion. So you get a
Metacidosis?
yes, normal anion gap metabolic acidosis. So whenever someone is given too much normal saline, 0.9 normal saline, they get a normal anion gap metabolic acidosis, also known as the hyperchloremic metabolic acidosis. Okay, argon. Where do you see argon? Argon is actually very important in medicine. You saw this before, right? Lasers. Used in photocoagulation of patients with diabetic retinopathy.
Okay.
You haven't seen this yet. You can search out, see, make sure I'm not bluffing you.
Yeah.
Look, if a guy tells you sweet things, what will you do?
Say thank you.
No. Check it out. He's trying to con you, lah. Girls, guys are just trying to con you. Okay. NDYAG lasers. Used in? It's usually in your ophthalmology textbook.
Yeah.
Yeah. So it's used in your photocoagulation. It's one of the most common ways of generating lasers. So it stands for neodymium. Where have I seen neodymium before? Yes, neodymium is in my bentonite series. Okay, neodymium. Okay, Y is your yttrium. Hey, where have I seen yttrium? Yttrium is here, right below scandium, above lutetium. Okay, so it's actually one of these rare earths. Okay, aluminium, garnet, okay, crystals. So they use this to generate lasers. So when you talk about, okay, NDYG is neodymium, yttrium, aluminium, garnet, lasers. Okay, so that's crystal used to generate the laser. Okay, so when you have the laser is light application by stimulant of emission radiation. Laser is actually just an acronym. So they use the radiation, and then because once it's if you harmonize the same frequency, then the laser will actually become, the amplitude will become more powerful, and then they use it, becomes very high energy, so they use it to burn, okay, all the new vessels. Alright, so you sacrifice a bit of vision to prevent the destruction because the new vessels will burst. Alright, so your YAG lasers, argon lah. Argon is used in the generation of these lasers. So argon with this one, neodymium, and then they use it to generate lasers. Potassium, essential for life. Calcium, again, essential for life. Calcium moves into your bones. Alright, so what is strontium? Strontium is used for? They used to give strontium for patients with osteoporosis. Because strontium actually is the same, just below calcium. So you take the strontium, they actually will replace the calcium and strengthen the bones. Now they don't use it so much anymore. Alright, barium. Barium is used in your barium swallow.
Mm-hmm.
All your barium swallow and all, it goes into your stomach, it goes into your barium enema, and then you get to see the outline of the gut. All right. Radium is from radon. Francium, okay. Cesium is used to make your atomic clock. Okay, so that's how you get accurate time. Rubidium, not so much used in medicine. All right. Radon. Where have you seen this before?
X-ray.
No. Radon is a risk factor for. Have you, you're in second year, right? Oh, you haven't done your clinical years already. But if you read lung cancer, what is radon? So there are a lot of places on Earth where there's a release of radon is stored. So when they dig into the ground, radon is released, and when radon is released, you breathe it in. Actually, it predisposes you to lung cancer. So people who are, it's one of those occupational lung diseases, they're exposed to radon, miners and all, they're exposed to radon, and high risk of developing lung cancer. Okay, so there are places that have rich radon, those people who live in those areas will have a higher risk of lung cancer. Radon breaks down into radium. Okay, so again, no, all these things like, hey, do I need to know this? Of course you need, because there's actually a lot of all these things. Okay, bromine used in your bromide, used to wash your wounds. Iodine is again one of those nutrients used to make your antiseptic, but also your thyroid hormones require a lot of iodine. Okay, and then of course people with hyperactive thyroid, what do we do with them? We give them radioactive iodine. So this radioactive iodine will be absorbed by the thyroid, but it doesn't release a lot of radiation, so it just releases a bit, so it kills off the thyroid. And then you don't have because it's easier to kill off the thyroid and just replace it with L-thyroxine. Very easy. Okay? So iodine very important. Astatine, tyrosine not used so much. Selenium, also one of your micronutrients needed. They are very smelly. Thorium, polonium, not so much, but they are smelly, Okay, smell like garlic apparently. Okay, then after that, arsenic, poison. Napoleon who's gonna watch Napoleon? Yeah, Napoleon apparently will die. It was in the wallpaper. They use it for wallpaper, get a very nice green. So apparently Napoleon got stomach cancer from the exposure to arsenic. Okay, and he died. So why is it only guys? Girls don't watch Napoleon. See, girls don't watch Oppenheimer, they watch Barbie. Yeah, they don't like historical dramas.
That's a bad stereotype.
But are you planning to go watch Napoleon?
No.
See, it's true anyway. Correct or not? Okay, I know you didn't watch Barbie but still, you're not going to watch Napoleon. Huh?
No.
You going to watch Barbie?
Haven't yet.
Are you planning to? Are you planning to watch Oppenheimer?
Yes.
Oppenheimer. You're gonna watch Barbie before you watch Oppenheimer, isn't it? Oh lah, it's like all this. Yeah, I want those Oppenheimer guys. Yeah. All right. Anyway, so arsenic, antimony. Again, also one of those things. There was an antimony mine in Sarawak. Used to mine antimony in Sarawak. Do you know that? And you claim to be from Sarawak. It's in geography.
I found the geography, so.
What?
I didn't take geography.
No, Form 1, Form 2 geography.
Yeah, that one.
Yeah, it's in Form 1, Form 2 geography. Antimony, there was antimony. So antimony is used for, very important, treatment of leishmaniasis, protozoa. All your meglumine, your stibogluconate, those are all antimony based agents. Okay, and antimonials. So it's very toxic. Okay, look, it's below arsenic, so it's very, very toxic. All right, but it's useful because it's also toxic to the leishmaniasis, protozoa. Okay, and after that, bismuth.
Pepto-Bismuth.
Yes, Pepto-Bismuth. Okay, and bismuth actually also have antibacterial properties. It is actually the heaviest. Actually, they used to think that it was the heaviest element that is not radioactive, but it turns out that there is a bit of slight radiation. So now, lead is the heaviest element that is not radioactive. That does not have a radioactive radioactive isotope. So bismuth is used bismuth is in your quadruple therapy. So after you fail all the first line, second line triple therapy, you use bismuth. Okay, bismuth has antibacterial property, and of course it's anti-acid. All right. So thallium is poisonous, indium, gallium, this one is used in chips and all. Alright, and then you have your nihonium and all, not used so much. Alright, rutherfordium, dubnium, seaborgium, borium, hessium, all these are, they are in such small amounts nobody knows what they are. Alright, titanium, you use in your titanium plates. Titanium is highly non-reactive, used in your refractor, you use in titanium. Zirconium, you use cubic zirconium, artificial diamond, things that look like diamond but they're not diamonds, that's why you use to fool a girl, like give her zirconium. Yeah, pretty cruel lah, but still. Yeah. Hafnium is just good. Neodymium, as I talked about just now, used to, actually neodymium is also used for magnets, so to make very, very powerful magnets. So your magnets is measured in Tesla, so all your MRI, you actually have neodymium inside. So actually you need a lot of all these things to live your modern life. You think an MRI just comes out of the sky like that. Okay, tantalum. Tantalum is actually a side product of I forgot silicon is stannum. Stannum is tin lah. Malaysia used to produce a lot, now not so much. Okay, and it's also essential for public health because you use it to coat all your food. Because of tin, you can actually put food in the tin, preserve it, and actually prevent hunger. So people rarely die of hunger, even if there's a famine, it's because they cut food from reaching the area. The Ethiopian famine was actually largely man-made. Plumbum is lead. So lead too much can cause lead poisoning. The other thing is plumbum is they use, all this if they put it in the glass and all the collars, the gastroenterologists wear a lot of it, cardiologists, because they are exposed to a lot of radiation, so they use it to protect themselves. Alright, and then so tantalum used to be one of those breakdown, those side products of, but nobody knows how to use it, so they just throw aside. Then they realize it's very important for the production of handphones and smartphones. So now tantalum actually has more value than stannum itself. Yeah, it's a funny thing, isn't it, that used to be a waste product. See, there's no such thing as a waste. The only thing is a waste is something that we do not know how to use it yet. But once you discover a use for it, it's no longer a waste. In fact, it's more precious than the original product it was, which was a byproduct. Okay, chromium, you use the chrome, your car fender bender looks nice. Okay, molybdenum, tungsten. Tungsten is the one that's really, really hard and high melting point, so they use it to make weapons. Yeah. Alright, manganese. Manganese is sometimes a micronutrient. Technetium. Technetium is actually very important.
Nuclear imaging, right?
Yes, nuclear is used a lot in nuclear imaging. So you get this 99. Technetium is the lightest element of which all its isotopes are radioactive. So bismuth is the heaviest, of which none of them are originally thought none, but actually turned out that one, so now it's plumber. But technetium is all of its isotopes. So you have this thing called 99M, technetium. Okay, metastable. So usually radioactive things are not very stable, but by the balance of the neutrons and protons, is actually pretty stable and lasts long, maybe a few hours. Usually most of them last seconds to milliseconds, but this one actually lasts hours, 99M, so they call it metastable because it's very stable for radioactive material, and it's used in all your scans, like the SESTA-MIBI scans. Okay, and all. So they are so fluorine also, yes, you have your 18 fluorine, R-fluorodeoxy, glucose FDG. Okay, so this one is used to PET scan. This one technetium usually they use for SPECT. So what's the difference between a PET scan and a SPECT? PET scan is a positron emission tomography. SPECT is a single photon emission computed tomography. So what do they mean by single photon? Single photon is a quantity, okay, package of energy, which is a gamma ray. Okay, so what you do is, when 99 Technique, they actually release gamma rays. So you have a camera that picks up all these gamma rays, and then so you take the SESTA-MIBI and all, you'll localize to where you want it to be. Hello, Father. Okay. Praise the Lord，我哋好快就搞掂。OK，拜拜。 Okay, so actually PET also have a gamma camera. Okay, they pick up gamma camera, and PET actually is higher resolution than your SPECT. But why? It's all in the name lah. So what happens is SPECT is a gamma radiation. So this one releases gamma, whereas 18FGT releases a positron. So this one is by beta decay. Positron. So when one positron reacts with positron plus electron, you will get two gamma rays actually. So that's why it's a higher, it has higher resolution than your SPECT. So PET and SPECT, they are not the same. Hey, why does it sound the same? Why they so? Because this one has a lot of protons, so it tends to release. It breaks up. 18FDG breaks down by beta decay. This one breaks down by gamma decay. Okay, gamma decay releases one gamma ray, one photon of gamma ray. But 18FDG releases proton. It reacts with one electron, releases two gamma rays. So it has higher resolutions. PETs have higher resolution than SPECT. And then you combine so that's why people with SPECT combine with SPECT CT, you can PET combine with PET CT, you can combine with MRI, SPECT MRI, PET also you can combine with MRI to provide the imaging, and then you superimpose the two images together, and then you get a clear image of what is going on. Okay, what is the active part? So if you have infection, your PET will be active. If you have cancer, the PET will be active. So it's actually, so it all goes back to chemistry. So your chemistry goes back to chemistry, goes back to physics, and it makes everything actually very interesting. Yeah. So when you understand that these are not just lists of names, and actually based on their chemical properties and all. Yeah. All right. Let's go on. So technetium. Okay. Now you know all your technetium system, EB scans and all that sort of thing. All right. Rhenium, not so much. Iron, of course, you need iron, part of hemoglobin, carry oxygen. Okay. Then ruthenium, that's why I use osmium. Osmium is used in what? Osmium, come on, where have you guys been exposed to osmium? It's there, you see it all the time. Electron microscopes. You need osmium to fix, and then you treat the cells and whatever you want to look under the microscope with osmium, and then after that you use it to take your electron microscope. So you need osmium. So osmium is very important. Cobalt is radiopharmaceutical. Okay, rhodium. Rhodium is actually used to make white gold, so it's actually more valuable than there's fake white gold. So you get a girl a rhodium ring is worth more than a white gold ring. But girls can't tell the difference actually. They don't know. Yeah, they don't know that rhodium is more valuable than platinum. Okay, then iridium. Iridium is also one of the densest, higher melting point. They used to have this satellite system called Iridium. This was before Skylink. What was the name of Elon Musk punya, the one, the satellite one? Starlink. This was before Starlink. So they tried one with Iridium, but it was too ahead of its time. So it died a natural death. Not enough people use it. Okay, nickel, palladium and platinum. Platinum is used in your cancer treatment, cisplatinum and all. They all have a platinum moiety in the center. Copper, of course, if you got too much overload of copper, you got Wilson's disease. So remember, you see this thing? Copper, argentum. Bronze, copper is used to make bronze, silver and gold. That's how you remember this one, this column. Okay, argentum, again used in some of your stains. Okay, and gold is gold used in treatment of rheumatoid arthritis. Zinc is also one that's used for all your zinc, some of your enzymes in your body, all the zinc fingers and all. Okay, cadmium gives you heavy metal poisoning. Mercury, used to measure millimeters of mercury Okay, and of course we remember Minamata Bay What happened? Minamata Bay. Do you know Minamata Bay disease? Never heard of Minamata disease? I thought it was a classic in public health. Minamata disease, because they dump the mercury into the bay. Suck out the mercury, and when people eat, they all get a neurological disorder and brain damage from the mercury. So mercury is also used to make felt. So that's why the Mad Hatter was mad. Okay, because he was exposed to mercury. So you see, all these stories are actually you don't just read it. If you actually read the science beneath it, it's actually very, very interesting. Alright, mercury. Oh, let's go into mercury a bit. Okay, so your normal right atrial pressure is 2 to 4 millimeters of mercury, isn't it? What is your normal GVP?
3 to 5.
8 to 12 centimeter of water. Correct? How many times is mercury more dense than water?
13.
Okay, so 12 centimeters is about 120. So 8 centimeters is about 80 millimeters of water lah. Okay. So if you wait, sorry, I think I overestimated this a bit. This one is a bit raised already, and it should be 5 to 8. Okay. So if you assume it to be like what you call 5, so it would be 15 lah. So okay, so if you assume it to be 33 min, so it should be equals to 3 min. Let's say assume between 3. So 54. Okay, or actually 3.5 lah. 3.5. So 50 divided by 3.5. 13 point something, isn't it?
Yeah.
And that's how much more mercury is more dense than water. So of course, if you use water to measure right atrial pressure, it will push up even higher than compared to mercury. That's why you use mercury for a sphygmanometer. Because if you use normal water column to measure your normal human pressure, you need a water column this high. Okay, but because you use millimeter mercury, it's much lower. Okay, so again, is the weight of 3.5 millimeters of mercury is equal to 50 centimeters of water. That's why the pressure push, because this is less than, so it can push up higher, but once the weight is equal to the pressure, then it cannot go up any higher already. You're in equilibrium. Okay? Alright, so mercury and then rutherfordium, dubnium, okay, all these are just a bunch of names lah. Let's go to the lanthanide series. Lanthanum. Lanthanum is actually one of the rare earths also used in your okay, so if let's say you have hyperparathyroidism, so what do?
Resect.
Well, if you cannot recite, if let's say the guy says I want to take some medication, you can try to suppress it. Okay, so one of the ways of suppressing it is using lanthanum. Okay, lanthanum, but they don't use it anymore because it's a rare earth lah. Okay, neodymium I talked to you is used in your magnets. Promethium, samarium, europium, gadolinium, very important. Gadolinium is used in your
MRI.
yes, MRI is used as the
Dye. Contrast.
contrast in dye. So it's actually part of the lanthanide series. So if let's say patient got renal impairment, you give gadolinium, what will happen? You got renal impairment, you give lanthanum, there is a risk for developing the no, worse than that. The renal failure is due to something. So you get the retrocranial fibrosis that leads to renal failure, and actually patient can die. Yeah, so gadolinium, you don't give gadolinium patient renal impairment. You cannot just simply do MRI, you have to make sure that's why knowing what is the patient's liver function, renal function is so important. You don't, I want to scan. For what? Okay, I need a scan for this. This is the patient's blood, renal function, liver function. Okay. Actinium, not so much use in medicine. And that is the periodic tables of the elements in a nutshell as used in medicine. Okay? Thank you very much. Yeah, okay, we can stop the recording.